Today we're going to talk about section 9.4 in your textbook, and this is another set of tests we can use to determine if a series converges or diverges. And these are called the comparison tests. There's two new tests we're going to learn here, and in my opinion, these are probably two of the most useful tests we're going to learn in this chapter. Let's just do a quick summary of the tests that we have learned so far that we can use to determine convergence or divergence of a series. The first one we learned was the nth term test, and you'll recall that said if you take the limit of a sequence that represents the series, if it goes to anything other than 0, then the test diverges. The geometric series, of course, we can look at the R values and see what happens. Telescoping, where we can write out the terms and see if there's a limit for the nth partial sum. P-series, so if we have a series in the form 1 over n to the p, we determine what it does based on whether p is greater than 1 or less than 1. And then, of course, the integral test, if we have a series that is positive, continuous, and decreasing, when we look at its corresponding function, whatever the integral for that does, so does the series. So the two tests we're going to learn today we call comparison tests. So first I want to look at this. We have the series 1 over 3 to the n plus 2. And I want you to think about if this would converge or diverge. This looks really similar to 1 over 3 to the n, which we know converges because it's geometric and r is equal to 1/3. What does this series converge to? Converge to 3/2. If we did a over 1 minus r here, we would get a value of 3/2. Consider this. Since 3 to the n plus 2 is greater than or equal to 3 to the n for all n, then do you agree that 1 over 3 to the n plus 2 would be less than 1 over 3 to the n? Think about that for a second. The denominator here is larger than the denominator here, therefore this fraction is smaller. So if we know 1 over 3 to the n converges, and we know 1 over 3 to the n plus 2 is always less than or equal to 1 over 3 to the n, what do you think that tells us about the convergence of 1 over 3 to the n plus 2? Here's a little picture. So 1 over 3 to the n, that's the one that's in red. 1 over 3 to the n plus 2 is the one that's in black. So what I want you to notice is that if the series on top converges, then it forces the one below it to also converge. So we would know 1 over 3 to the n plus 2 converges. So we call this the direct comparison test. So make sure you write this down. This is the test itself. So let a sub n be a positive sequence, and it let be less than or equal to b sub n for all n. If we know by some other test that b sub n converges, then that forces a sub n to also converge because it's below b sub n. On the other hand, here's a picture of it. I'm sorry, I forgot I had this in the PowerPoint. So this is just a little generic picture. So suppose that b sub n is the one in red, and we know a sub n is below it, the one in blue. So if b sub n converges, it's forcing the one below it to also converge. But on the other hand, if a sub n diverges, since b sub n is above it, it forces b sub n to also diverge. So this is kind of the opposite case. Same inequality. If a sub n is less than or equal to b sub n, and we happen to know a sub n diverges, then anything above it would also diverge. Little picture representation. A sub n is now the one in red. If it's diverging, then anything above it must also diverge. All right, so let's look at an example. Determine the convergence or divergence of this series. So we have 2 to the n over 3 to the n plus 5. So you would need to think about, is there another series that looks similar to this that I could do a comparison with based on size that I do know something about? But you'll observe that this looks similar to 2 to the n over 3 to the n, which is really the geometric series 2/3 to the n. And think about this relationship. 2 to the n over 3 to the n is always larger than 2 to the n over 3 to the n plus 5, which is the series we are interested in. So if this series is less than this series, and we know that this series converges because it's geometric and r is less than 1, what does that force 2 to the n over 3 to the n plus 5 to do? We would say that our series converges by direct comparison test. And the comparison was to the 2 to the n over 3 to the n, which is geometric. Okay, let's try this one. We have 1 over 2 plus the square root of n. So think about what series this might look similar to that we do know something about. This resembles the p series 1 over square root of n, or 1 over n to the 1/2. And we know that that diverges because p is less than 1. So what is the relationship? What is the inequality between our original series and this new series, this p series? Our series is less than this p series. Now think about if that helps us, because this p series, diverges, but it's above the series we're interested in. So since this diverges, does that tell us about anything below it? It does not. So this doesn't help us to use the 1 over n to the 1/2. But think about maybe if there's another p series we could use. 1 over n, that's the harmonic series, remember. We know that that diverges. And see if you agree with this inequality. 1 over n is always going to be less than or equal to 1 over 2 plus the square root of n. Think about powers here. The square root of n is always going to be smaller, which means this fraction is larger. The 2 is not going to be consequential here. So if 1 over n diverges, and that is less than the series we're interested in, what does it force anything above it to do? It also diverges. The reason is by direct comparison. The trick when you're using a direct comparison test is to find a series that you can make an inequality with that makes sense to you. Now the next comparison test we're going to use, I think, is actually a little bit easier because you don't always have to come up with these inequalities and these relationships between the series. It's called the limit comparison test. Make sure you write this down. This is an important test we're going to use a lot. Suppose that a sub n is positive and b sub n is positive. This only works for positive series. And suppose that the limit as n goes to infinity of the ratio of a sub n over b sub n equals some number L, where L is a positive finite number. Then the two series either both converge or both diverge. They have to do the same thing. So let's look at an example. Show that the general harmonic series diverges. So this would be any series in the form 1 over an plus b, where a and b are both positive numbers. Well, we know that the basic harmonic series, 1 over n, is divergent. Of course, that's your p series again. So let's do a limit comparison between these two series. So we're going to do the limit of 1 over an plus b over 1 over n as n goes to infinity. And if we do the reciprocal here and simplify, we get 1 over a for the limit. A was positive. This is a positive finite number. So what does that tell us? Since 1 over n diverged, that means our new series, 1 over an plus b, will also diverge. And this is by the limit comparison test. One thing I want to mention here is that the ratio in which you put these two series to calculate this limit makes no difference. Had I put 1 over n over the 1 over an plus b, my limit would have just been a instead of 1 over a, which is still a positive finite number. So the ratio, the order you put those numbers in, or that sequence in, does not matter. The limit comparison test works very well for comparing an algebraic series with a p-series. A lot of the times the p-series is what you're going to want to use for a limit comparison. Let me show you what I mean. Suppose we want to look at this series. An easy comparison would be to use 1 over n squared. 1 over n squared converges. P is greater than 1. And if we did the ratio with this, we'd get a positive finite number because the powers would be the same. So that tells us our series converges. Take a look at this series. Think about what you could compare this with. This looks algebraically similar to 1 over square root of n. And what does that do? We know 1 over square root of n diverges because p is less than 1. So if we put a ratio of these two, we'd get a positive finite number, which indicates that our series also diverges. Try this one. This is similar to n squared over n to the fifth, which is really the same as 1 over n cubed. We know 1 over n cubed converges. So if we do a ratio with that and our series here, we'd get a positive finite number, which means our series converges. Okay, let's try this one. Determine the convergence or divergence of the series. We have square root of n over n squared plus 1. Think about what p series this looks close to. We could compare it to the square root of n over n squared, which is the same as 1 over n to the 3 halves. And what does 1 over n to the 3 halves do? It converges because p is greater than 1. So we're going to go ahead and take the limit comparing our series to the 1 over n to the 3 halves. Again, whichever one you put on top makes no difference. I could have done this in reverse order. When I simplify it, I get this. Make sure you see that. Take the reciprocal of this and flip it, multiply to the top, and make sure you see that this simplifies to this expression. And the limit for that, of course, is 1. That's a positive finite number. What does that tell us? Our series converges by the limit comparison test. One last one. We have the series n times 2 to the n over 4n cubed plus 1. And let's try comparing it to 2 to the n over n squared. Think about what this series does. First thing we always should try when we have an unknown series is our nth term test. So if you take the limit as n goes to infinity of this new series, you would get infinity, which of course is not 0, so that means that this series diverges by the nth term test. So let's take our series and do a limit comparison with 2 to the n over n squared. Little algebra here simplifies and gives us this. And since those powers are the same, the limit for this will be 1/4. So since the series I compared it to diverged, that means our series also diverges by the limit comparison test.